Hi everyone, welcome to week 2 of machine learning and causal inference. Just to get everyone up to speed, last week, you had a crash course on machine learning. Just a reminder of what are some of the widely used methods in machine learning, what people are doing out there. I imagine that for most of you, that was a review, or mostly a review. Now is when we get into really the core of this class, that is how you can use and deploy machine learning-based methods in causal analyses. This week, we're going to focus on a more of a classical topic in causal inference, estimating average treatment effects. I'll say more in just a few asides about what that means and how we can rigorously deploy off-the-shelf type machine learning tools for this task. In the upcoming weeks, we're going to dig deeper and look at some more specialized tasks, including treatment personalization, and look at how we can kind of develop special purpose machine learning methods for those tasks. So anyways, before saying anything else, just of course the core tension of this class, and one that both Susan and I have already emphasized many times, but it doesn't hurt to say once more, is what's machine learning about? Machine learning methods are about prediction. They're about, given a type of data, understanding what usually happens in a given situation. For example, you could download historical weather data, and then based on that data, try to understand, given the conditions you expect there to be tomorrow, what's the chance that air pollution levels will be dangerously high? That's prediction, but that's not usually what we care about in many economic or social science applications. In many applications like this, we care about causal questions. We don't just care about understanding what would usually happen in a given type of situation. We want to understand counterfactuals. We want to understand, say, what would happen. Not only do we think tomorrow might have high pollution levels, but can we change this by, say, reducing the number of cars on the road? We're most interested in interventions we might take to kind of improve the situation. So this is obviously a different kind of question. And as we'll see many times in the class, a naive application of machine learning methods that are designed for prediction to causal task can get one into quite a bit of trouble. But as we'll also see, if done right, then actually machine learning methods can be usefully adapted to causal tasks and can be very helpful. So anyways, having said that, this week, our goal is to understand how machine learning methods can be rigorously deployed for the classical task of average treatment effect estimation. And with this, the main result, we're gonna give it in the fourth part of this lecture. The main result is going to be a methodology based on double robust estimation that can kind of take as inputs generic black box type machine learning estimates, and as output give you confidence intervals with kind of a limiting normal sampling distribution and all the guarantees you'd like. But okay, we need to work up to it. And so this will be done in kind of 4 videos. The first video, in this one, I'll introduce the notion of average treatment effect, talk about some basics about how we can think about average treatment effects in the context of randomized trials. Then in part 2, I'm going to talk about kind of some simple ways you could think about using machine learning for average treatment effect estimation. Compare that to kind of classical regression-based methods and see what's good, what's bad, what the limitations are. The spoiler guess this is not really a spoiler alert, the naive method won't quite work. You'll leave something on the table, you won't get the confidence intervals of the type you'd want of the naive method. So we need to do something else. And here, we're going to start working towards it. Part 3 may feel like an aside at the time. I'm going to introduce propensity score methods and kind of an estimation toolkit built around that. But by the time we'll get to part 4, you'll see that this was not an aside. The kind of state-of-the-art way of incorporating machine learning methods into the average treatment effect estimation world kind of combines the naive approach with insights from propensity score-based methods. That's going to take us to what's called the double robust methods. And out of all the methods I'm going to talk about today, that's the one I recommend you use in practice. And that's one I also use often in my own research. All right, so that's the outline. And now we're in part 1. So what's the average treatment effect? Here's a definition. I should emphasize, again, like we mentioned in the intro video, when it comes to defining core notions from causal inference, we're going to move quite fast in this class. So if you want more background on these notions, it may make sense to say, read some kind of introductory econometrics resources, including some of the ones we've listed on the syllabus. So, okay, for all of today, I'm going to work in terms of this classical statistical setup. We have n units, n independently sampled units. And for each unit, we observe a feature vector. That's kind of background information about who you are. A response y, that's the outcome, the thing we usually want to improve using a treatment. And then a binary treatment, it's 0 or 1, 0 if you didn't get treated or if you got assigned control, and 1 if you got treated. So this is a standard causal setup. And then in order to talk about causality, what I'm going to do here is I'm going to posit the existence of these quantities yi0, yi1. These are called potential outcomes. And the way to interpret these quantities is that yi0 measures the outcome you would have observed for the ith unit had they received control, and yi1 is the outcome you would have received for the observed for the ith unit had they received treatment. Then, of course, the outcome you actually observe, yi, is the potential outcome corresponding to the value wi of the treatment that you actually received. Why are potential outcomes useful? It's because they enable you to kind of very directly define a causal effect. The causal effect of the treatment is the difference in potential outcomes. It's for the ith unit, the effect of the treatment is just the difference between what would have happened to the ith unit with the treatment versus without. So this is the treatment effect for the ith unit. And a lot of causal inference is going to be trying to say something about these differences in potential outcomes. Now, today we're going to kind of focus on one specific question you can ask in terms of these potential outcomes, and that is, what is the average treatment effect, or what is the average difference in potential outcomes? If the causal effect of the treatment on the ith unit was yi1 minus yi0, then here the thing we're calling tau, the average treatment effect, is the average across the sampling distribution of these individual treatment effects. And the average treatment effect is, not surprisingly, often considered kind of a first very helpful summary measure of the effectiveness of a treatment in some population. So why is this problem not completely trivial? Well, taking averages is not that hard. We know how to do that. And here the difficulty, of course, is that you have a missing data problem. For each unit, the treatment effect for the individual treatment effect of the ith unit, yi1 minus yi0, is defined as the outcome you would have gotten if you were treated minus the outcome you would have gotten if you weren't. That's the difference of two things. But of course, you only ever get to observe one of these two things. Either you're treated, in which case you observe the treated potential outcome, or you're control, in which case you observe the control potential outcome, but you never get to observe both. So you have this fundamental missingness issue. That's what makes this problem not trivial. On the other hand, for it to be interesting, it also needs to be possible. And it turns out that kind of given the right methods, estimating average treatment effects is tractable. So where I want to work towards, like I said earlier, this week is getting to a point where we have kind of more complicated types of data, and we can kind of bring machine learning tools to the table to kind of enable flexible and robust estimation of average treatment effects in quite a bit of generality. But just as a warm-up, let's talk about the simplest case in which you can estimate an average treatment effect and how that works out. And of course, the simplest case for doing causal inference is the randomized trial. We say that you're in a randomized trial if the treatment assignment is randomized. That is, there are some people who get treated, some people who get the control assignment, and it's really who gets treated or control is chosen completely at random. There's kind of no association between the potential outcomes of a unit and the treatment. Qualitatively, you could think that it's a randomized trial if for every person you flipped a coin, if the coin came out heads, you assign them to treatment, otherwise you assign them to control. And okay, why do we like randomized trials? Well, here's kind of a very short derivation, which shows that essentially the average treatment effect, that is the average difference between the kind of treated potential outcome and the control potential outcome, this thing here can be expressed as in this other way, that is the expected value of the outcome for the treated units minus the expected value of the outcome for the controls. And of course, this thing here is easy to estimate. This is, you could just kind of literally in the randomized trial, take the average of the y's for the treated units and this for the controls. So this kind of immediately suggests an estimator that you could use for the average treatment effect. And of course, the important difference here is that here we define expectations in terms of potential outcomes. Potential outcomes are not always observed, so we have a missing data problem. Down here, we have a conditional expectation, but in terms of yi's, that is kind of actual observables. There's no problem in estimating the average of y conditional on w equals 1. So this we can just read out from the data, and there's no problem. And really, the key step in this derivation here was this first line, where we argued that the average of the treated potential outcome over the whole sample is the same as the average of the treated potential outcome conditional on wi equals 1. And this follows from this randomization statement. Because treatment is randomized, conditioning on treatment doesn't change the expectation. So this is safe. Then in the second line here, we went from the expectation of the treated potential outcome conditional on being treated to just the expectation of the outcome being treated. This is kind of more mechanistic. Kind of, we already agreed that when you're treated, the thing you observe is the treated potential outcome. So this is kind of a more tautological consequence of the definition we've set up. But so what does this mean? It means that even though there's this fundamental missingness problem in causal inference, you have treated and controlled potential outcomes. Causal effects are defined in terms of differences of the things you can only ever observe one of. Then it's actually possible to estimate an average treatment effect using a randomized trial. That is a data set where treatment was generated uniformly at random. All right, so just to kind of illustrate this in terms of kind of a simple example, suppose again that we wanted to understand the effect of driving restrictions on air quality. So what I'm showing in this slide is essentially oracle data that kind of an omniscient statistician could hope to have. Every day you have yi0, the pollution levels you would have gotten that day if there were no restrictions on traffic. yi1, another potential outcome, that is the pollution levels you would have gotten with the traffic reduction. And then this tau I, that is the effect of the traffic reductions on pollution that day. Here, I made a plot of the potential outcomes yi0 and yi1. You see that there's very strong correlation between yi0 and yi1. That is, most days pollution was what it was going to be, and kind of the traffic restrictions only had a kind of second order effect. But at the same time, you also see that yi1 is typically smaller than yi0. The data kind of lives below the diagonal. And this means that kind of the traffic reductions did help, the restrictions did help reduce pollution a little bit. And if you take the averages of all these, then what this says is the average treatment effect, that is the average daily effect of the traffic restrictions, is here -10 in the units of the problem. If we had access to this full table, getting this -10, just averaging the tau i's, would be very easy. But of course, this isn't what real data looks like. In real data, even if you had the kind of best data you could hope for, you have a randomized trial, then every day you flip a coin. And depending on how that coin comes out, you either observe yi0, the control potential outcome, or you observe yi1, the treated potential outcome. You don't get to observe both. And so in particular, your problem is that you never observe tau i's. So you might be wondering, how can I estimate the average of the tau i's if I never get to observe a single tau I? But this is kind of the theorem we just saw earlier. You get an unbiased estimate for tau I by taking the average of the outcomes on days where you got treated minus the average of the outcome on days where you got control. And then this gives you an average treatment effect estimate of -10 here. All right, this is how it works. Randomized trials are very nice. Not much need for kind of, you can do most things you want in randomized trials, at least in terms of estimating average treatment effects without using any very sophisticated methods. But okay, we're not always in randomized trials, and then we need to work harder. And we're essentially a very kind of simple example where this kind of discussion from the couple last slides wouldn't apply is if the treatment assignment isn't random, but is actually associated with confounders. So let's just consider a very simple example. You want to understand the effect of some treatment that helps mitigate and prevent obesity on quality-adjusted life years. But you didn't assign this treatment in a randomized trials. Rather, you just have data from electronic medical records with decisions made by doctors as they saw fit. And here you might assume that, look, doctors aren't going to assign the treatment kind of uniformly at random. They're going to prioritize this treatment to people who have higher weight coming in. And if this is what's going on, then just taking a difference in means can fail to give you a valid notion of an average treatment effect. So kind of, let's consider an extreme example. Let's suppose the treatment does nothing. So for every unit, the treated and control potential outcomes are just the same. But here you see kind of people vary by weight, they vary by outcome. There's here negative association. And what is the only effect that's going on here is essentially that doctors are more likely to assign treatment to people with higher weight than with lower weight. And what's going to happen here? Well, you're going to have some treated units that live in the higher weight region, controls who live here in the lower weight region. So kind of the treatment does nothing, but if we start looking at a difference in means type estimator, we look at the average outcome for treated units versus controls, what are we going to get? Well, the average outcome for the treated units here, for the control units here, is higher than for the treated units. This is just a function of doctors choosing to treat different people based on weight, and there being negative association between outcomes and weight. And when you put these two things together, you see that actually the average outcome for treated units is going to be lower than the average outcome for the control units. So if you just kind of naively study this as a randomized trial, you'd think that the treatment here was harmful, whereas actually it does nothing. You just had a selection bias issue, and you're kind of detecting that bias. So this is the end of the first part. In the second part, we're going to start talking about conceptual and statistical solutions for estimating average treatment effects when you're not in a randomized trial.